everyone. Welcome to today's show, where I'm joined by two guests, co-authors of this book, which is inverted on my camera, but I think Phil's got the non-inverted version in his background. I'll put links to it in the description if people are interested, but we're going to be talking about the themes and things behind this book. I think people in my audience are going to be very familiar with you, Phil, and your kind of work around physics and cosmology. But Niayesh, do you want to kind of introduce yourself, what you do, and your background?
Sure. Hello, nice to meet you. I'm Niayeshi Afshordi. I'm a professor of physics and astronomy at the University of Waterloo and associate faculty in Perimeter Institute, where I'm sitting right now in Waterloo, Ontario, in Canada. And I work in astrophysics, cosmology, physics of gravity, quantum gravity, and everything in between those.
Awesome. And then just for people who don't know, Phil, what's your relationship to Niayesh and this book that you've done together?
Right. So I started making films on competing models of the early universe, interviewing all the leading figures like Stephen Hawking, Roger Penrose, Alan Guth, and Niyayesh's name kept popping up. And I kept seeing it in papers about early universe cosmology. And what's amazing about Niayesh is that usually, like a cosmologist I interview, they've probably made like a model of the Big Bang. But Niayesh has done like loads of them. So I thought, I've got to speak to this guy. So eventually I ended up interviewing him at the Perimeter Institute for Theoretical Physics. And we hit it off and said, you know what, we should sort of turn this topic into a book. So that's how we sort of hooked up and how this book came about.
And then just for you, I guess, Phil, as well, you've kind of come to this topic, I guess, partly through apologetics, but is there a personal interest in physics outside of that kind of guided you into this domain as well?
Oh, no, I was interested in astronomy first, I would say. In fact, I didn't know anything about like William Lane Craig and the Kalam argument until I was in university. I went back to college to study astronomy. And it was only when one of the people on my course said, let's go to this debate. And it was the William Lane Craig versus Stephen Law debate. And that was my sort of being thrown into this world of sort of dealing with Christian apologists and their claims about the Big Bang and so on. At least that's how I remember it anyway.
And Niayesh, how have you found the kind of apologetic space that's using the physics? So is that something you were familiar with before talking to Phil? Has a lot of that stuff been kind of like new to you, and what's your experience of that been?
It's kind of interesting. It's not something that I was really thinking much about going into this. I mean, of course, I do come from a very different background. I grew up in Iran, and when I arrived in North America, more than 20 years ago, basically the previous century, I had kind of my own baggage from my own upbringing, and that was just shortly before 9/11. When 9/11 happened, then everything kind of went upside down. But then I had there was a version of apologetics that was going on and back home in Iran, the Islamic version, and then I kind of met some of that online here, but not too much. I used to have a weekly debate with a seminary student back at Princeton, where I was a student, where we're kind of trying to explore things that are in common between Quran and Bible. But this idea of apologetics is kind of interesting, that it does appear in different guises, but in very different holy textbooks. So yeah, that's. But really, that was kind of well in the background, and it kind of came back to the fore when we started writing this book, and back towards the end of it.
And so in terms of the title, Battle of the Big Bang, I'm guessing that publishers had something to do with that. But what is it that you were hoping to communicate with the title? Who's the target audience? What are the main kind of themes that you wanted to get across with this book? And that can go actually for both of you, but maybe, I don't know, if one of you had more of an influence on that than the other, feel free to.
I mean, you go first.
Okay, the original title that we had was actually more of a question. It was what banged? But some people loved that. Some people hated it. I know, I had a friend of mine who worked in marketing. He says, do not go with that title. But then, Alex O'Connor liked it. He said, you should stick with that title. So there was a bit of a divide, but the publishers suggested Battle of the Big Bang. And it's actually really appropriate because there are lots of battles that we describe in the book. There are battles, of course, Nathan, you're going to be more concerned about the apologetics battles, but there's lots of battles within physics that have preoccupied me. And I've hosted debates between physicists, so not like Christians versus atheists, but more like cyclic universe versus inflationary universe and string theory versus loop quantum gravity and things like that. So so there's lots of battles that we talk about. The main battle, of course, is to describe correctly what happened at the Big Bang. And we know a lot about the history of the universe. We can go back quite close to the Big Bang, but not close enough. And so what we want to do is push the envelope of our knowledge out further. And that's where the battles lie. Any time where there's uncertain science and the frontier of science, there's going to be rivalries. And certainly, when I made the video series, it was very much to explain the science only. And as soon as we decided we're going to write the book, so we're going to make it quite different to the video series, the Before the Big Bang YouTube series that I did. So one of the things to make it different was to tell stories. And it's the rivalries between the scientists that's super exciting, I think. So who is the book aimed at? It's aimed at a lay audience, but a lay audience that's interested in, these big questions. Where did the universe come from? And, people that read like popular science books like, Brian Greene and Brian Cox and people like that, people that watch PBS Space-Time and Sabine Hossenfelder, that's the target audience.
Awesome. So you sort of start the book with, oh, sorry, did you want to say something, or feel free?
Are you asking me? No, I don't have much to add. I just want to say, Phil, in fact, I remember the first draft of the book that I remember, it started with a battle. I think it's now still in there, but it was this battle that was going on during, and then an eclipse happened that was predicted supposedly by Thales. So battle, I think it was going on in Phil's mind from the very beginning. And I think one thing that's interesting, and I think Phil did mention a lot of battles, but this battles between apologetics and scientists and amongst the scientists, I think it's kind of interesting to contrast those and we kind of highlight, the similarities and differences, because there is a spectrum that kind of, it's not that like one stops at one point and the other, we turn from one to the other. There are a lot of kind of ideas that have turned into dogmas even in science, and we want to highlight that it's not just religion that have dogmas.
So I guess in the sort of narrative arc of the book, obviously, you go through some stuff that people were saying a long time ago, kind of motivating various ideas around, these big themes of origins and the cosmos and stuff. But I guess the scientific part of it really starts in the sort of late 19th, early 20th century. Could you sort of paint a picture of what the state of physics was like, the field of cosmology, if it's even understood that way, and what sort of ideas are knocking around at the start of the kind of scientific journey as we would understand it?
Yeah, why don't you take that one?
Yeah, right. Okay. So the beginning of 20th century was basically a revolutionary time in physics. So in 19th century, we had basically kind of flourishment of Newtonian physics. Newtonian physics kind of had done whatever that it could have done. We had fluid mechanics, we had understood planets. So everything was kind of as well as it could have been with Newtonian physics, but then there were cracks started to appear. And in early 20th century, within a span of 20 years, basically Newtonian physics that was a few hundred years old at that time turned upside down. We had quantum mechanics, and then we had general relativity. So physics completely changed in a very short period of time, and that was kind of the beginning of cosmology, modern cosmology as we know it. In fact, the most famous event that happened was we actually realized that our galaxy is not. It's not the entire universe. We don't actually live in a static universe. Our galaxy is one of many, tens of billions, and they're all moving away from us. as discovered by Edwin Hubble, and based on kind of astronomical developments that was discovered by Henrietta Swan-Leavitt. So that was the birth of cosmology and birth of Big Bang. That's basically started from kind of in parallel from observational developments and from theoretical developments. Theoretical developments was Einstein's discovery of general relativity. And then observationally, we discovered that the universe is expanding. And then putting these two together, many scientists, including Lemaitre, for example, who we talk about a lot in the book, discovered that there must be something like a Big Bang, which is the birth of the universe.
So one of the big things that you talk about in the book is sort of like this theory of ether, right? That's around. Could you talk about what that theory is and what kind of overturns it initially?
Oh, yeah. So ether is of course, there's a historical context to it. It's I can't remember. I think it's the fifth element. Is that right? I mean, I don't know that my.
I think that might have been like quintessence or something, but maybe it's something there. Yeah.
Okay, I actually don't remember what's the earliest occurrence of ether in history. Phil, do you remember that?
Oh, well, I think the idea of quintessence was, that was what space was made of. Like. But they thought there were different rules for the universe, right. Like what we would consider outer space. They would just call it the heavens. They wouldn't have had the same conception in the ancient world. But that was the material, because that was all perfection, whereas things were imperfect down on the earth, so they had to have a different substance.
But what about the ether?
So the ether, I think, would go back probably to Maxwell, I guess. When Maxwell came up with his equations, light was something going through a medium. So I think it goes back that early, but I'm not sure, to be honest.
Yeah, so I think this actually goes back. I can't recall exact history. I mean, I remember there was this idea of gravitational ether back in, I think, even due to Laplace and others, that kind of gravity mediates through a medium, because there was it's kind of weird that things gravitate from far away, and nobody was really, Einstein wasn't happy with it and others weren't. So maybe they thought there was some ether that gravity goes through. But I think ether, the idea of ether as something that fills the space, kind of goes way back. But I think the most kind of a prominent place where it came in the history of science was the idea that, okay, so everything should propagate, every wave that we know, like sounds, like water waves, they propagate through some medium. And then Maxwell discovered through basically early developments in electromagnetism in late 19th century, Maxwell, Faraday, and others, they discovered that light is electromagnetic waves, and basically you have lots of electromagnetic waves. And there was this question of, okay, so what do electromagnetic waves propagate in? There must be some sort of a medium. And the greatest discovery or greatest insight that Einstein had that led to discovery of development of special relativity was that maybe light is an exception. Basically, electromagnetic waves were exception, that they don't really need a medium. So ether was kind of proposed as the medium for electromagnetic waves, or in particular, I think luminiferous ether, that was the word that was used. But it turns out that discovers, in particular through Michelson-Morley experiment, that even if you move, the speed of light doesn't seem to change, unlike other types of waves that if you move, like you start running, the sound waves could move faster or slower, basically depending on how fast you run with respect to them. So light is different, and that led to the revolution in physics, that basically maybe time is not absolute. So that led to the theory of relativity, and eventually it led to the theory of general relativity, which integrated gravity into the equation.
So is the main way that this was connected to sort of cosmological thinking that ether provides this sort of absolute medium that's like almost a part of a reference frame for the entire cosmos or something? Is that the main idea?
That's right. Yep. So before Einstein, basically in Newtonian physics and Newtonian thinking, and some also say Galilean thinking, there was an absolute notion of time. So time ticks everywhere in the universe. There's maybe you may call it the cosmological frame, and time ticks in all of that. And then that also is the medium in which light propagates. The speed of light is with respect to that frame. But then basically about Einstein, the first thing that led to the development of a special theory of relativity was this discovery that maybe, in fact, this came from studying Maxwell's equations, because Maxwell's equations that describe electromagnetism, they seem to have this weird symmetry that if you kind of mix space and time in a particular way, the equations don't seem to change. And that seemed to suggest that maybe time is not absolute, it's actually relative. So this was discovered by Lorentz. This is called Lorentz transformation. But eventually Einstein made sense of all of this, that maybe there is no absolute time. Different observers experience time differently. But there are other things that may be absolute. So Einstein, in fact, proposed that the speed of light is absolute. Then every observer, no matter how they move, they always experience the same speed of light.
So yeah, it's difficult, I guess, to talk about each of these bits in isolation because they're all relatively connected to each other. But then, so Einstein's coming up with general theory of relativity, special theory of relativity. I mean, those are sort of connected to the ether thing, as you've already outlined. But what else is kind of going on in terms of the things that Einstein's coming up with? And I guess, importantly, how are these ideas connected to how physicists are broadly thinking about cosmological origins at that time?
Well, I think the important thing is what Einstein discovered in his equations was that the universe was unstable. Now, actually, believe it or not, this was already known in Newton's theory. But Newton sort of thought he had a fix for it, which was to make the universe infinite in space and time. Turns out that fix didn't actually work, but he thought it did, and it was thought to work, but it didn't actually work. So in relativity, again, we see that the universe is sort of unstable. In fact, you can go all the way back to the ancient Greeks. They had this idea that the universe would be unstable. If you go back to Empedocles, he thought that love brought everything together. So if everything was brought together by love, then the universe would sort of collapse on itself. So he had like hate as this sort of repulsive force.
The problem of evil solved.
Exactly. Yeah. So the idea has plagued cosmologists for a very long time, thousands of years. But yeah, when relativity came out, it was shown that the universe would either be expanding or contracting. Now, of course, famously, Einstein added his cosmological constant to sort of try and keep the universe stable. But once the universe was found to be expanding, then it did away with the cosmological constant. Wrongly, though, because it turns out, 1988, we discovered that there is either a cosmological constant or something close to it. It might not be an actual constant, and recent discoveries are maybe hinting at that. So the bottom line was, I think the most important thing is, with general relativity, scientists suddenly had the tools to model the evolution of the cosmos, and they could see that it was evolving. So you had the tools coming out, and then the observations that backed that there was an evolution. So that was the birth of modern cosmology.
And I guess, is there any information on sort of like how, because my understanding, for example, of the reception of Einstein's work is that, it's not kind of like instant, right? Like some people are quite resistant. They've got their own ideas and theories. There are some observations then that come along later that confirm things. Not everyone's on board. They think, oh, maybe there's something up with this. And it takes quite a while for people to generally be on board. I mean, is that the right sort of idea for what's going on in cosmology as well? Does it take a while for people to really start taking these ideas on board in their modeling? Or
I think there's two sort of answers to that. One is taking relativity on board, and two is taking cosmology on board. So relativity, I think, when special relativity took time, I think, to get widely accepted. General relativity, I think, once the eclipse expedition came out, it was reasonably widely accepted. Of course, there were quite a few German scientists who were anti-Semitic, and there was a letter published by like 100 German scientists condemning Einstein. And he said all it would take was one fact. He wouldn't need 100 scientists. So there was some anti-Semitic resistance, but I think generally amongst physicists, relativity was broadly embraced. But cosmology, not so much. I think the view was that cosmology wasn't even science, that the questions were too big, that they couldn't really be tackled. I think it was Rutherford that famously said, I don't want to hear anyone using the word cosmology in my lab. Then we had Dingle, who was I think the president of the Royal Astronomical Society, and he bemoaned people for talking about universe mania. Now we see bloggers write about multiverse mania, but then it was universe mania. And they just thought that this wasn't a proper science. There wasn't any data. So yeah, you could write down equations and model the expansion or contraction of the universe or something, but it was just very poor in observations. But I think that changed with the discovery of the cosmic microwave background. Then I think it was taken a lot more seriously. And then with precision measurements of the temperature differences in the cosmic microwave background, now you have a very precise science. So that's the sort of evolution, I would say.
So maybe just before we come on to that, I believe in your sort of timeline, there's a bit before that where the term Big Bang is sort of introduced as well. I don't know who would be best again to sort of field this question to, but I believe that comes about through like a radio show. Is that right? The term Big Bang, and then it kind of catches on. Do you want to say a little bit about that? Whoever would be most appropriate for that one, because I don't know.
Phil, you go.
Okay. Yeah. So basically, the phrase has a bit of a history. I think Eddington was the first to call it a bang. He said, "I refuse to believe the universe began with a bang." Then actually, I discovered this recently. Actually, in the 1940s, just after World War II, there was like a German military installation on, I think it was on the island of Heligoland, which is actually the island that quantum mechanics was discovered on. This is where Werner Heisenberg went to sort of think about quantum mechanics, and he came up with his version of it. Anyway, the Allies wanted to bomb it after the war because it was very heavily fortified. And they used the term Big Bang as the name of the operation. This was, I think, in 1947. I think it was Heligoland. I have to check that. But then, Hoyle used the term on a radio show, and he was basically trying to describe it. He was like the science popularizer of his day. Think Brian Cox, think Brian Greene, think Neil deGrasse Tyson. Hoyle was the public face of science, or at least astronomical science in Britain in the 1940s. But they didn't have TV back then. They didn't have YouTube. They had the radio. So he said, I was reaching for a metaphor that would explain different models. So we had the steady state model, which was, his creation. Well, I say his creation. I mean, he worked with Bondi and Gould. And actually, it turns out Einstein came up with it first, but he never published it. So people didn't know that Einstein came up with it. But so that's the idea. Now, later on, people started saying it was come up with as an insult. But this is not true. There's no evidence for that at all. So that's basically a myth. Everyone I've seen just repeats it over and over again. But there's no evidence it ever was an insult, and Hoyle denied it was an insult. He was trying to popularize science and come up with a colorful metaphor. And so he came up with that term. Before that was the primeval atom. That was the term that Lemaitre had come up with. But that didn't catch on so well as Big Bang. It's just a much more colorful term. And that's a term we've got stuck with. But there's a very good reason to think Big Bang is an excellent description. I'm going to pass that over to Niayeshi. Why is Big Bang a really good term?
Yeah, definitely. I just want to say, I like both primeval atom and Big Bang. Actually, I want to bring the primeval atom back for different reasons. I had published a paper recently. I said, okay, primeval atom is actually very good. But that term hasn't been used in a long time by professional cosmologists. The Big Bang, though, I really like it because, not many people realize it, but the best evidence that we have for the Big Bang is the cosmic microwave background, but more specifically, these fluctuations in the cosmic microwave background that Phil was talking about. And these are like precise predictions of the theory that's kind of been matched very well with observations. These fluctuations are actually sound waves that presumably have been generated at the Big Bang, and they propagate and then oscillate, and then we just see the acoustic oscillations. They're called actually acoustic peaks, literally acoustic peaks, the things that we see in these fluctuations. And yeah, so bang produces sound, a very loud sound, and indeed Big Bang was the biggest sound was ever produced, presumably in an observable universe.
Would you mind, sorry, just clarifying that for me? Again, I'm not a physicist, so but I'm working with some, low-level sort of understanding. If space is a vacuum, when you say sound waves, do you mean what do you mean by that? What's kind of oscillating there?
Right, but the space is not a vacuum. There is matter in it, and that's basically what banged, right? So there was a primordial plasma that was very hot and very dense. And as it turns out, there were sound waves that are moving around in it. So it was kind of, you could live there. It was loud. It was this humming that was going around, right? And the universe expanded, so the density goes down, and there were these sound waves that are moving around. At some point, these sound waves kind of stretched and become basically very, very long wavelengths, much longer wavelength than the sound wave that you and I can hear with our ears. But they're kind of imprinted in a structure on the distribution of gases and temperature. So now we wouldn't call it sound wave anymore, but they started as sound waves. They kind of froze at some point when they went down. The frozen is kind of like fossils of the Big Bang now.
Just a question, by the way, Phil, is Niayeshi's internet sort of maybe breaking up a little bit for you, or is it just from my point of view?
There are a couple of moments where the sound cut out for a fraction of a second, but
okay, it's okay. Okay,
yeah.
Cool.
So one thing I want to add, Nathan, is just remember that the universe was much denser in the past. So, like right now, outer space is very
there is
different to what it would have been back then.
I guess what I'm trying to figure out is the observation here. So is the general observation, you sort of like look around, right, at all the stuff that there is, and you kind of see this overall sort of pulsing signal coming from things, and then you sort of in terms of your explanation, you can explain that by things were closer and there was a lot of energy that caused that, and these are and that's like the best explanation of that observation. Is that broadly right then?
That's correct. Yeah, I think I'm back now, I think, right?
Yes. Yeah.
Very good. Yeah. So I think one analogy that I have is, imagine I'm sitting in this room and then someone is talking next door, right? And if this room is vacuum, I'm wearing some oxygen mask or something, so I cannot hear what's going on outside. But then I could still kind of use a camera and take image of the wall, and if I could film the vibrations of the wall, I could actually decode what's being spoken in the room next door. And that's kind of the way we kind of can listen to the Big Bang, not by directly hearing the sound waves, but rather by looking at the wall, basically where it was denser back then, and those sound waves were propagating more effectively. So we can actually map those sound waves now through the cosmic microwave background, so we're not seeing the sound waves, or we're not detecting the sound waves directly, but we're kind of measuring them indirectly.
And so is that what then motivates people to begin to think there's sort of scientific confirmation of a kind of origin point or something like that? Is that the main kind of confirmation of that idea?
That's certainly one of them, but I mean there are many probes. That's this measuring of the sound waves is one, and as we go into great length in our book, there are others. One kind of holy grail of Big Bang cosmology is detection of gravitational waves, which are fluctuations in geometry or fabric of a space-time. That's also another prediction of Einstein theory, which have been detected, but not from the Big Bang. It's been detected from black holes merging together. Whether those kind of waves are generated in the Big Bang, that's the subject and basically the topic of intense inquiry and observational surveys.
So I guess at this point in the book, that's where a lot of these different theories kind of start popping up, right? That people are talking about. I mean, in terms of the field of cosmology at the time, could you give me a sense of how people pick this up and start theorizing about it? So is the idea there that people want to start just building these like rival models at that point, or is there not much pluralism in terms of people's thinking prior to that?
Prior to when, though? When are you thinking, Nathan?
Prior to the CMB sort of observations and, inflation becoming a kind of idea that's widely accepted.
Well, let's just go back to the history. So in the 1940s, we have this rivalry between the steady state and the Big Bang. So the steady state pictured the universe was expanding, accepted that the universe was expanding, but there would be sort of new matter created in between the galaxies, if you like, so that overall everything would just be steady. So the Big Bang said no, everything was hotter and denser in the past. So they had this thing called the perfect cosmological principle, that basically the universe is is uniform over space and over time, whereas the Big Bang was a sort of imperfect cosmological principle. Maybe it's uniform over space, but not over time. Well, think of it this way: as obviously if we look back, things are older. We're seeing further into the past. So in fact, we will. So although you might have a sort of uniform universe, a homogeneous universe, I should say, and isotropic, but the key point is it would be different, hotter and denser in the past. That's the Big Bang, basically. Big Bang is hotter and denser in the past. Steady state, same level of density in the past. So that rivalry existed, let's say mid-40s to mid-60s, but by the discovery of the cosmic microwave background in the mid-1960s, I think the steady state, or at least the version of the steady state that we know of by Bondi Gordon Hoyle, was disproved. So then what happens is that roughly the same time in the mid-1960s, Penrose and Hawking come up with these theorems. They're called singularity theorems. I mean, they already knew about singularities before Penrose and Hawking, but they were seen to be reliant on very dodgy assumptions. But this singularities idea that the density, the matter, the density, the curvature, the temperature, things like that, they would all go to infinity, and it's sort of a stopping point for the trajectory of light rays. So first Penrose developed this. It was already known in black holes. In fact, it was Oppenheimer and Snyder that worked on this. And if you see the movie Oppenheimer, they actually passed around the paper, but that's what that paper was about. They don't actually mention that in the film. But what everyone thought was, oh yeah, but they assume like perfect spherical symmetry. So, and that's unrealistic. So probably this idea of singularity was just an artifact of having this super unrealistic assumption. Then Penrose comes along in the mid-1960s and says, I can derive this without that assumption. We can relax that assumption. There's still going to be a singularity. This was in a black hole. Then Hawking comes along and says, I can turn your theorem upside down and show there was a singularity at the Big Bang. So then this idea of the expanding universe or the Big Bang universe, if you like, gets coupled with the Penrose-Hawking theorem, and then we say that's the origin of time. So this was reasonably a consensus, I would say, and there was nothing to really rock the boat till the end of the 1970s, and then we come on to inflationary cosmology. So I don't know if you want to go into that, or if you want to pause there and you want to.
Unless there's any of the physics that you want to expand on around that, Niayeshi, or feel free. Yeah.
Right. It's kind of the way that science works is kind of we try to come up with the theory, and I mean in this case theory of general relativity and quantum mechanics, and we then look at the universe, look at observations. In this case was the cosmic expansion and cosmic microwave background, and then use the theories to kind of extrapolate. And that means that kind of take these and push them, see how far they go. And this happens, and it happens all over the science. So the singularity theorem are kind of seem unique because it maybe tell us about our cosmic origins and creation, and basically there are all sorts of kind of metaphysical implications of them. But at some level, they are like what happens all the time in science, that we have an understanding of a system and we push it until it breaks. And the singularity theorem was the breaking point of our assumptions. Realize that basically our theories, if we push them there, they don't make sense. We need something new, a new theory. And in fact, the fact that we needed a new theory was already evident from, I mean, decades earlier, that we had these two theories of quantum mechanics and Einstein general relativity, but they didn't really talk together. If you try to kind of describe a phenomenon using both of these, you kind of come up with nonsense. So you either kind of have to use one or the other one, and hope that kind of you don't have to use both of them at the same time. Or, I mean, you have to be very delicate, basically. They don't want to play nice together. So that was kind of the problem, that we already knew there was something going on, and the singularity theorems, when it was further evidence that something was going to go wrong, at least at the Big Bang and inside black holes, potentially elsewhere, who knows? Maybe cosmic acceleration, is dark energy or cosmological constant, have something to do with quantum gravity. We don't know that either. But then there were kind of more details of the cracks that became clear in 1980s, and that's what Phil was starting to talk about. Is basically that led to development of inflation. That why is our universe so uniform, so homogeneous, for example, so isotropic? There is not enough time to kind of communicate from one side of the universe to the other side. So Phil has this analogy that if you put up pizza, if it's just hot and bring it out, it takes a while for it to get cool. But then the universe hasn't had that much time. It's a very big universe. So that's the biggest problem. And there were others that it kind of didn't make sense in the theory of the Big Bang as we knew it back in late 1970s. And that kind of set the stage for the next revolution that came in early universe cosmology.
So just to make sure I've understood the problem, sorry, it's that the theories would predict that you'd have more, things would be hotter than they are or colder than they are. Sorry, just because I don't have a good model.
they would be either one, because basically, imagine I'm sitting this right. So I want to come up with an analogy, right? Imagine, so I have like this cup of coffee and has coffee in it, and I have another cup of coffee and has coffee in it, and they have exactly the same temperature. Okay, so you say, okay, how do they have exactly the same temperature? Maybe they were like together in the same oven for a while, or in the same microwave for a while, and then we remove them at the same time. Okay, so that requires some time for these to actually communicate either with each other or with the same microwave, right? But then if you look at the Big Bang theory, it seems that basically where this cup lived and where this cup lived, they were so far apart that there was not enough time for them to actually communicate with each other. So somehow the universe set some absolute temperature everywhere. And remember, this also goes back to this thing that Einstein discovered 100 years earlier, that, well, more than 100 years, that, I mean, there is no preferred frame. So there is no absolute time. The idea was that everything is relative, there is no ether. So why would these two cups have absolutely the same temperature? They haven't had time to communicate. There is no absolute time. And that was the mystery. It was called the horizon problem, basically, that there's the finite horizon where kind of cups could talk to each other. But then these cups happen to have the exact same temperature, much, much beyond basically the horizon where they could talk to each other. So that was the horizon problem.
And just could you link that to a few ideas maybe that are just in the background of my bad physics thinking about this? So is that related to where some people talk about sort of action at a distance or something like that, or how? And also how are physicists? What sort of units are physicists thinking of this in terms of? Is it temperature, Kelvin? Is it entropy? Is it all of the above sort of thing?
Kind of all of the above. I mean, it's all the properties seem to be this kind of homogenized across the universe. What was the first thing you asked?
And when people talk about like action at a distance, right? Is it related to those sorts of ideas, or is that a sort of different?
Yeah. So this action at a distance is, in fact, the thing that Einstein was the most uncomfortable with, but when he developed his theory of general relativity. And of course, I mean, or special relativity for that matter. But the special relativity, I'm kind of trying to track I can't remember exactly the history, but there was this Coulomb repulsion of the basically charges that it seemed that kind of two charges could repel or attract each other at some distance. But really, through the theory of electromagnetism that Maxwell developed, we realized that it's not really an action at the distance. There is this electric field that the charge is interacting with, and this electric field propagates. So it's not instantaneous, right? And then Einstein kind of generalized this for gravity, that gravity cannot act at a distance either. It's really the geometry. Instead of electric and magnetic field is the geometry that's kind of, you should think of it as some sort of a substance or medium, and that kind of can propagate. So as this force, the gravitational force that we experience from Earth or from the moon or from the sun, is not really action at a distance, but in fact our interaction with the local geometry, and this local geometry can propagate at the speed of light. And so this was all built into the theory of relativity, that action at a distance is a no-no. It's kind of cannot be physical. Everything propagates, interacts locally. And yet we had this weird non-local thing, not necessarily in the laws, but in the setting up of the initial conditions of the universe, that basically things that are very far apart are the same somehow.
Right. So the idea is that that's kind of putting a constraint on your explanations, because you can't just explain the uniformity by like weird action at a distance. It's got to be something when stuff's closer. Is that right?
Well, that's a good question. I mean, I think then there's kind of a roundabout, but I think towards the end of the book, we come to the conclusion maybe that's one possibility, that ultimately there could be action at a distance. So in fact, this faster than the speed of light travel, or what we call it, the chapter called the speeds of light. This is the idea that maybe the Big Bang, in fact, a speed of light is not an absolute limit, can be much, much faster. And as you approach the Big Bang, it approaches infinity. So maybe, in fact, early universe or high densities or high temperatures, that's when you can have action at a distance, or at least very, very far away, because those are different. And that's kind of one approach, in fact, to quantum gravity now. It's known as Hojava-Lifshitz, that maybe what unites quantum mechanics and gravity is the idea that at the fundamental level, there is action at a distance. There is a speed of light is not really a limit, but somehow at low energies or larger scales, it appears to us that there is a limit. Same way, for example, it appears that sound wave might be a limit when we are talking to each other. But when we start seeing each other, we see that, okay, the light propagates much faster. So maybe, yeah, that's an illusion. So that's kind of that's one possibility. It's a proposal. It's not proven in any way. But certainly back in 1980s, that was not something I was considered very seriously. And then people wanted something that seemed more consistent with Einsteinian point of view.
Right. So that's probably where we should bring in inflationary cosmology, Nathan, because
yeah,
the idea in the 70s, some of these problems started to appear. So we had this horizon problem. There were others. We won't have time to unpack them all, but there was like the monopole problem, the horizon we mentioned, the flatness problem. There was the origin of structure problem. So there were all these problems with the Big Bang. And in 1979, two scientists, Alan Guth and Henry Tai, were trying to fix one of those problems. This was actually a different problem called the monopole problem. And they found that, if you have a very rapid period of expansion, they called it inflation, how rapid, usually the numbers given, I think, in Guth's book was that the universe would double in size in 10 to the minus 37 seconds. So very fast expansion. That would solve the first problem, the monopole problem. And it was after that Guth very quickly realized it would solve one of these other problems, the flatness problem. And actually at the time he'd never heard of the horizon problem. And it wasn't until, he was having lunch with some colleagues that someone mentioned the horizon problem to him, and he quickly cycled home and went, I wonder if this new inflation will solve the horizon problem. And indeed it did. And the reason, the mechanism for solving it is basically the universe would have been much, much smaller in the past than in the standard conventional cosmology. So the sort of two bits, the two cups of, was it coffee or tea now? These two cups would have had time sort of to
it's
come
coffee,
in.
coffee, yeah.
It's coffee, okay then. It would be tea if it was at my house. So basically the universe would be much, much smaller in the past. So they would have had time to communicate, as it were. That solves the horizon problem, and it's thought to solve all these other problems. So people were extremely impressed with inflation, and it had this sort of rival theory, because it also was an attempt to explain how we get all these structures in the universe. The alternative theory that was being pushed around at the time was called cosmic strings. So that there were these objects. Think of, when you take a water and you freeze it becomes ice. So you get all these cracks and imperfections. So it was thought that maybe the structures in the universe formed something like that. And inflation, was clearly the winner in this battle. The observations from the cosmic microwave background strongly disfavored this cosmic strings approach. So then inflation became the sort of mainstream, sort of dominant view amongst cosmologists. But one of the things there's been some pushback on, it's thought to lead to a multiverse. Once inflation stops, it can never. Once inflation starts, it can never stop. So basically, inflation ends in one patch of space, and that is actually our Big Bang. And this is the interesting part, because a lot of textbooks say that inflation happens after the Big Bang. But in fact, Niayeshi did a survey of cosmologists, not of cosmologists, of physicists. It was at a big black hole conference with a lot of leading figures. And we asked them a bunch of questions about controversies in physics. So like, how do you explain dark matter? How do you explain dark energy? What do you think about the fine-tuning problem? And the only question that they agreed upon, when I say agreed upon, like I had a majority vote for, was that the Big Bang should just be understood as the theory that says the universe evolved from a hot, dense state. So it shouldn't be understood as it evolved from a singularity, or that it had a beginning of time, anything like that. It just is the theory that says the universe evolved from a hot, dense state. But here's the kicker. In inflation, the universe is cooled down, and it only heats up after inflation ends. So then when inflation ends, that's when you get the hot universe. That's the Big Bang. That sense, then, inflation is actually a pre-Big Bang scenario. And then there would be this field, this inflating field. It's called the inflaton field. And these other pocket universes would form out of it. And here's the irony. This picture, they call it eternal inflation, is actually very, very similar to the steady state model. So in some sense, the steady state has actually come back through the back door. So then, of course, some people love this idea of the multiverse. They like it because maybe it solves a fine-tuning problem, or maybe they just like it because it's kind of cool. Wow, there's all these universes. What an amazing idea. Other scientists loathe it. We have people like George Ellis. We have one of the creators of inflationary cosmology. I mean, Guth was the main guy, but actually the version of inflation that Guth came up with didn't quite work. So then it had to be sort of modified, and Paul Steinhardt was one of the key developers of that modification. But he eventually turned against the theory of inflation. The multiverse being, there are many problems. We go into in detail in the book, several problems with inflation. But I think the one that was the main motivation, certainly for Steinhardt, was this idea of the multiverse. So that he thought that, well, if you have an infinite number of universes, then how do you do probabilities? How can you say, the theory predicts anything? Because it's going to say, Goose says,
predicts everything.
Yeah, exactly. So then you'll run into a real quagmire of, well, what does it mean to say that inflation predicts anything? And there's a lot of back and forth, and that's what we delve into the book. So that's one of the big battles. Inflation is the leading candidate, but can it solve these problems, or do we look for an alternative? And the VSL idea, variable speed of light theory, is an alternative, because you could say back at the Big Bang, everything was expanding really fast. That's one solution, but it's not the only solution. Maybe the speed of light was much faster rather than the expansion rate, and they would give you kind of similar solutions. A third alternative is that there was a contracting universe before there was an expanding universe, and it's advocated by some that could similarly solve some of these problems. So this is where the one battle is inflation the right model, or do we have an alternative? How do we fix all these problems that inflation brings up? Do you fix it within the theory, or do you go to an alternative? So that's one big battle.
And so in terms of these other models as well, so you talked a bit about the multiverse there, but I guess there's sort of like cyclical models that you bring up. And there's
Oh,
kind
Nathan,
of like
you're English. Why are you saying cyclical? I thought we said
cyclical. Yeah,
it's
yeah.
the Americans that say cyclical, isn't it?
I've been influenced. Yeah, I've been affected by Americans. So yeah, in terms of these cyclical models, and I guess there's like, you know, crunch expansion models. I remember when I was in like in high school that was kind of all the rage that people talked about. Is it the same? Is the same primary consideration inflation for those, or are there kind of like other big drivers in terms of theory choice between these different models? Like, and if so, what are those kind of the biggest kind of considerations?
I think it depends on who you ask and which cyclic model you're talking about. So Steinhardt and his collaborators, the most recent version, he's worked with Anna Ias, their motivation is definitely get an alternative to inflation. Like very clearly, that's the motivation. Now, there was a precursor to their current version of the cyclic model, which was maybe slightly less motivated as an alternative to inflation, or they definitely presented it as an alternative to inflation. But the idea was, can we get ideas from string theory into cosmology? And some of those ideas coming from string theory seem to back inflation, but others seem to say, no, we don't need inflation. So the precursor to the cyclic model that Steinhardt's now using, that was trying to imagine like these brains, these sort of extended objects that the universe is supposed to be embedded in. So that cyclic model was inspired by that. There's another one called string gas cosmology that was inspired, I think, well, let's use string theory and analyze the Big Bang. Oh, we don't need inflation. Roger Penrose has a cyclic model, and I think he was definitely an opponent of inflation. There's no question about that. He didn't like inflation from day one. But from talking to him, I spent a lot of time talking to Roger about this. My understanding is that he was more actually trying to solve the entropy problem. He thought there had to be something that puts the universe into a low entropy state. And so he came up with this idea called conformal cyclic cosmology, which is not bang, crunch. It's more like expansion to infinity, and then the universe forgets how big it is, and then it transforms into a hot, dense state. So it's not recollapsing. And he thought that this conformal geometry could, one, resolve the singularity, but could also explain the low entropy problem. And then also you won't need inflation. But I think the entropy one was his motivation. So people have different motivations. Like I've interviewed a lot of the people that have come up with these different cosmologies. And definitely some had, like, actually one amusing example was Andy Albrecht. Andy Albrecht was he was Paul Steinhardt's student. So he wasn't like all anti-inflation Andy. I think Andy's like sympathetic to inflation, but he was like, that was the first thing he ever did as a scientist when he was like a PhD student. He goes, I couldn't have solved cosmology with the very first thing that I did. So he was keen to work on alternatives to inflation. He worked on the variable speed of light theory. But even then, you know, he was a little bit more skeptical than some others were. So people have different motivations, I think, for coming up with different models.
Awesome. Oh, sorry, Niayeshi, were you?
Yeah, I was just going to say, I think as someone who's been kind of witnessing this inflationary battle like firsthand for, I mean, more than 2 decades now. In fact, I was there at Princeton when Steinhardt kind of was starting to turn against inflation. I remember first I visited, he was kind of, he still liked inflation, but he had these reservations, and then kind of slowly he became more and more kind of radicalized against inflation. I kind of, I mean, there are some, philosophical considerations, but at the end of the day, I mean, you want to make progress in science, and then there is the problem. I mean, the thing that happened in the past 20 years is that whatever that we observed in the universe, right or wrong, there was some inflation model that was explaining it. There were some people who were pulling it. Of course, this is the right theory. Early on, Andre Linde, one of the first memories I have, or papers I read, at some point people thought universe was open, so the curvature was negative. So it's kind of the property of a space that in Einstein gravity it could be a spherical or saddle type. So, and then there was this model of open inflation. Now, inflation was presumably solving this flatness problem that made the universe flat, but apparently didn't have to. So that was So there was a time that observations seemed to wanted the universe to be open, basically saddle type geometry, and then there was a right inflation for that. Then at some point we discovered non-Gaussianity, which was basically there were somehow more hot spot than cold spots in the cosmic microwave background. And then of course there was the right inflationary model. I was explaining that. That was very natural. That turned out to be the wrong observation. So then people stopped talking about it. Then we discovered gravitational waves from the Big Bang, and then everybody thought, okay, so they're getting Nobel Prize for Alan Guth and Andrew Linde. This is great. That's the natural prediction of inflation. Everyone was happy, except that 6 months later, we realized it wasn't really the gravitational waves from the Big Bang. It was a dust in our own galaxy. So, but that didn't change people's mind on inflation. And still, there was other inflationary models that were very well. So it seemed that kind of is very flexible. No matter what we observe, there always the right inflationary model, and there's always the right people who can argue it. Of course, this is the one that we expected from the very beginning. So it kind of doesn't feel like science to me. I would like theories to be kind of be somewhat concrete, that at some point they could be ruled out. This kind of reminds me of religion, that of course, yeah, okay, so obviously this passage of the Bible is talking about the Big Bang, and this is talking about the quantum mechanics, and then this is talking. So it's kind of, yeah, if you could explain everything in that kind of logic, right?
Yeah, on that point, actually, there were a couple of things that you talk about in the book that I thought would be interesting to get you to maybe clarify as well. So I guess when people talk about theoretical physics, things that inevitably come up are topics like string theory and also holographic theory, which you talk about in the book. And I wondered if you could, I mean, I've got questions about both, but I'm just kind of conscious of time. I mean, the first one was you talked a little bit about holographic theory, and how you were initially, I believe, skeptical, and then came around to seeing maybe some use to it, and use in terms of how it helped you think about cosmology. Could you explain that? And just one particular feature I'm very interested in is also how you're talking about information, like what you mean by information as a physicist when you talk about holographic theory as well.
Okay, so I'm assuming that's a question for me, because I don't know if Phil was as skeptical of holographic cosmology or not at the beginning. No, I mean, naturally, I'm skeptical of anything new, especially anything that's fashionable and popular. I'm very skeptical of it. So that's kind of generally true in and outside, inside or outside science. But yeah, holography was very popular when I was just doing my PhD, so I had some skepticism of it. But I think more seriously, the problem with holography was it was kind of the way that it was originally presented. It was basically a correspondence of a theory with gravity and a theory without gravity, a quantum theory with and without gravity. The quantum theory without gravity was sitting on the boundary of this space that has a negative dark energy, basically. And then the theory with gravity was sitting in the middle, basically. And it seemed to be very mathematically successful, and there were like thousands of papers, and if not tens of thousands of papers on it over time. But it turns out that we discovered around the same time that our dark energy is positive, and there is no boundary to our universe. Universe, as far as the data goes, is homogeneous and isotropic. Everywhere is like everywhere else. So that setup seemed contrary to everything that we knew about cosmology. So that was kind of, as a cosmologist, it seemed that it was like too kind of too abstract or too irrelevant, basically, to our universe as we understand it. I mean, there might be some mathematical lessons in it if you believe in a string theory, basically, or some version of quantum gravity. But then I think over time, one thing that happened that came through my collaboration with my student Beth Gould and Kostas Askenderis and others was this picture might be a little bit naive when I say a boundary. The boundary doesn't have to be in a space. It could be in time. And then that actually starts to look much more like cosmology. Because there was a boundary in time. There was the Big Bang or singularity or something weird happened as you go to early times. So that actually is is a very relevant setup. That's not the setup that most people who work on this topic professionally talk about, but that's the setup that's most relevant for cosmology, because there was apparently a point at which the universe started. It was a point in time, and the space seemed to be more or less homogeneous with the tiny ripples, but maybe we could kind of use this holographic dictionary, this holographic setup with a boundary in time to describe what came out. And it doesn't exactly answer what came before, but in fact, it's as long as it could predict things for what comes out, that's maybe all you need from a scientific theory. And that was kind of the way I warmed up to this holographic description, that if you have a boundary in time rather than in a space.
And what was the main sort of empirical observation here? So I remember something in the book relating to black holes, for example. Is it that the observations of black holes are like spatially distributed, but there's some kind of like information theoretic concerns about?
Right.
Well, yeah,
okay. So that wasn't. I guess that's a kind of theoretical observation, if that makes any sense. But it's yeah. So I mean, we haven't really observed entropy of the black holes, but in some sense, as I was telling you, there were these two kind of giants of physics in the theory of space. There is quantum mechanics, and there is general relativity. And of course, black holes is one of the triumphs of theory of relativity that have been now confirmed as the first famous picture of the black hole. So there are these black holes that were predicted by Einstein's theory. But then you start to apply quantum theory to the extent that you could trust it to black holes. Weird things happen. For example, Hawking discovered famously that black holes aren't really black. They have some thermal radiation. And then, funnily enough, he even discovered, he and other collaborators discovered these laws of thermodynamics that we usually think about as like molecular systems or things that are made out of kind of micro things. There is a version of them for black holes, even though the black holes, there were no microscopic structure of them, or there were no black hole molecules that we knew of. But somehow from Einstein's general relativity, you could come up with thermodynamics for black holes. And there was basically a version of entropy. Somehow black holes have an entropy. Now, this cup has an entropy. That we learned that from kind of when we did thermodynamics in the 19th century. The bigger the cup is, the more is its entropy. In fact, its entropy, if it's heated up, imagine there is coffee in it. The coffee is finished, but imagine there is coffee in it. If it's hotter, there is more entropy. And if it's a bigger cup, there would be more entropy. In fact, goes as the volume. Now, that's we understand from physics of the molecules. But with the black holes, if you just apply these curious rules of general relativity, which has no molecules in it, you come up with something that looks like an entropy, obeys all the same laws of thermodynamics, except that it doesn't go as volume, it goes as surface area. It has nothing to do with the temperature of the black hole. It just depends on the surface area of the black holes. And that kind of led to this idea that maybe somehow, even though black holes are three-dimensional objects, all the information sits on their surface because their entropy, which is kind of counting how many micro things, tiny things. I mean, usually when we think of an entropy, that's what we've learned from from physics of the 20th century, is that entropy counts the number of tiny things that exist in something, tiny estates, micro estates, the technical word for it. But black holes, the thing that looks like entropy goes as their surface area. So that led to this holographic conjecture, basically the idea that maybe in a gravitational system, all the information lives on the boundary.
And this is where and this will link back to some popular piece of science communication I'm interested in, by the way. But can you help me understand how physicists are thinking of information here? Because I see a lot of, particularly when I think people reason about things intertheoretically between disciplines, I see a lot of equivocation on the term information. So say, for example, I'm particularly thinking of like cognitive science and stuff here. But in terms of Shannon information, that's defined in terms of the actual frequencies of character occurrences in the English language. But in terms of physicists and what they're thinking about in terms of information, like how is that operationalized? Like, what does it mean to you to think of information in this sense?
Right, good. So the original thinking was, so this cup, that when we talk about the entropy of the cup, we say, okay, so I see coffee in the cup. is like up to the, say, like a quarter from the top, how many configurations of molecules would lead to the same thing from the outside, which is basically a coffee cup filled a quarter from the top. So that's that macroscopic description. How many microscopic things can give you the same macroscopic description? So that's actually how you define entropy. You basically count all these things that from the larger scale look the same to us. That was the definition of entropy, but the information is a bit more general. So it's kind of, it is somewhat fluid description. So when we talk about the information, we kind of, there is this idea of quantum states, which is, it's a weird thing because, I mean, you could have a cat that's dead and alive at the same time, but that's a state, that's a possible state that in quantum mechanics is allowed. But so when we talk about the same information, the idea is that the same state, there is an identical, well, there's an identical description with on the boundary and inside, basically. So that's when we when we talk about the same information. But there are infinitely many definitions of information. And in fact, one thing that's happened over the years is that people come up with a dictionary which translates what we mean by information on this boundary to what we mean by information in the bulk. And they just may mean different things. So the way I want to think about it is not necessarily like the theory that holography is not really a theory. I think it's more of a dictionary, like you have two different languages. A language that has gravity in it, and a language that doesn't have gravity in it. And you try to come up with a dictionary that translates these things to each other. And these translations are never perfect, like when you translate from English to French or to Persian, which is my mother tongue. Yeah, no translation is perfect. Everything kind of is not, maybe feel a little bit different if I use it in English or in Farsi or in Persian. But the idea is that we try to find this translation, and sometimes it works better than others. But that's the way kind of it's gone. And the same goes with information, that we kind of try to define some version of information on one side and then say, okay, so there is this other thing that seems to translate to this, and you can call that information if you want. But basically, yeah.
So Nathan, and I want to know, are you asking because of someone like inspiring philosophy?
That was my next question was about to be. So yeah, feel free if you want to.
Very briefly, we won't have time to unpack all those ideas, but feel free to push them. But I'll just put a little plug in, because we had a whole panel discussion between Niayeshi came on. We had Dan Linford, who specialized in philosophy of physics, and Alex Malpass, everyone I'm sure will know, logician. And we talked about inspiring philosophy's ideas. And I think the bottom line, he tries to argue that holography proves that space-time is emergent, and then it must be emergent from a mind, and only a mind can put information into the system. So basically it proves God. And I don't think that there's any reason to take these ideas very seriously. Space-time emergent, I think, is more plausible. It's not something we know to be true, but it's something that is certainly taken very seriously. That's, it's a reasonable bet that may be true. But what would be emergent from? Not from a mind, from quantum states. So there's no need to appeal to a mind to put information into the system. That's just, that's the bit that I think we should not take very seriously. But the space-time is emergent. It's not known to be true, but it's at least plausible.
Yeah, I think that's why I was trying to push on that information point, because I guess one of the common misunderstandings I sort of see is maybe there's like a kind of naive idea of almost something like semantic information that's like a psychological sense of the meaning of words or something, and it's very different to the way that information is kind of operationalized in physics and stuff. So to try and maybe give people a bit of a sense of that. So yeah, I mean, I guess we've talked a lot about all these different models, right, in physics and stuff. I wonder if more broadly, you could talk then a little bit about you're reflecting on all this in terms of the kind of like aims of cosmology and what you're trying to do and the general methods and standards of success. And just to frame why I think that that's a very interesting question is because I'm wondering, how much of a distinction you might even think there is between what is being done in this type of theoretical physics and certain types of metaphysics that people might be doing, where it gets kind of very theoretical and kind of like broad in your general strokes of your theories.
Well, I would say that ultimately the way we're going to assess any physical theory is if it makes predictions that we can be tested against the data. So any of these ideas about the Big Bang have to meet that criteria for them to be accepted as something that I would say we would know to be true. However, having said that, before we get to that point, we have to develop the theories. So that gets to now a gray area, because before the theory is developed and it's tested, is it still science? So you can think of different sort of axes. There's like pseudoscience versus science.Hat's the difference? Now, the simple answer, that people will be familiar with is it's falsifiable. If it's falsifiable, it's science. If it's not falsifiable, it's not science. But it turns out it's actually a bit more complicated than that, because, you could add an auxiliary hypothesis and then save your theory even after it's maybe been falsified. So then you have to try and assess, well, how reasonable is that auxiliary hypothesis? Sometimes the auxiliary hypothesis you add is fine, and sometimes it isn't. So there's a sort of complicated back and forth. We go into this in the book, and it's a sort of philosophy of science. And now, falsification is certainly, I think, an important criteria, that you want your theories to be falsifiable. And if they are not falsifiable, that is a mark against them. But as you're developing them, you might not get them to the falsifiable point yet. An obvious example would be, Aristarchus came up with the theory of heliocentrism, that the sun was at the center of things rather than the earth. And it turns out, there are falsifiable predictions for how you might observe the phases of Venus that come out of, through a telescope, that come out of Aristarchus's theory. Well, of course, Aristarchus didn't know that. It took thousands of years for anyone to realize that. So, of course, we want to develop these theories. So then, the criteria becomes more like, we have this analogy, this phrase, Feynman's straitjacket. So, but what Feynman said was, science is like imagination in a straitjacket. So you can come up with speculative ideas, and that's okay. But you've got to be aware of all the observational constraints, and you're playing within those. And if you're playing within those, you can say you're doing science, but maybe we wouldn't say it's like a scientific discovery. We might call it proto-science. So that's like distinguished from like accepted science. You're developing theories, and of course you don't know if they're going to make predictions, because you're still working on them, and you have to go unpack the maths and see, is there that prediction? It might take a while for someone to realize the prediction is there. So I would say, to be accepted science, you have to make predictions that are tested against the data. But before that, there's this proto-science, and there the constraints are you in Feynman's straitjacket? Are you aware of all the observational constraints when you start developing your ideas? And so that can be distinguished between like pseudoscience, where you just use sciencey sounding words, but you're not really playing in a scientific game. So to me, that's what we need. And the last chapter in the book, we go into what observations that there might be in the future that we could actually put some of these ideas to the test, and maybe end some of the battles and declare a winner. But that's the hope. But ultimately, that declaration of the winner is not going to be done through metaphysics. It's going to be done through observations.
Awesome. And then I was wondering, maybe this is for Niayeshi, is like, what do you think the role of like creativity and imagination is in your work as a theoretical physicist?
Yeah, it's a blessing and a curse, because of course, whenever I come up with something crazy, you're afraid that people look at you funny. And it takes time to develop like a status of some sort. And then but then it's kind of a weird situation that you're supposed to come up with new things, but of course, maybe you may be making a fool of yourself, right? So But on the other hand, that's the way that science progresses. And I mean, I suppose everywhere in humanity, you need the status quo does work, but we need new ideas to make progress. And the status quo does work until it fails, right? So it may work for a day or two or a year or a decade, but at some point we have to move on and we need better things. So I think there is the imagination and creativity is a big requirement for making progress, because we need new ideas. And I mean, if history taught us anything, deeper and deeper theories of the universe kind of have very different shapes and forms and languages, like the language of Newtonian mechanics and quantum mechanics and general relativity. They all have been very successful theories over time, in their own time, basically, in their own domain, but they use very different languages. And it's a huge leap of faith to kind of invent these new paradigms, these new languages in new kind of worldviews. And of course, you could imagine there could be many others that one may come up with, and people have come up with, and turned out to have nothing to do with the real world, so we don't hear about them. But for the next revolution, we do need these new kind of new paradigms. The one thing I wanted to mention, I think there is also this distinction between proto-science and pseudoscience, is that you do have, I mean, the imagination is necessary, but it's not. That's the important thing. And at some point, the problem is that we, and it happens to the best of us, we get too attached to our ideas, and we may kind of have a hard time letting go, even if there is, let's say, data doesn't support it. And we kind of give some examples of these over the years that, in fact, the proponents of the steady-state universe, Fred Hoyle, and in fact, there's a story that one of the students of Fred Hoyle, John Narlikar, actually visited me about 10 years ago here at Perimeter, and he still was working on a steady-state universe. This was in 2014 or so, and he gave a talk why all the people who work on Big Bang, they're just following the fashion, and scientists need to be independent thinkers. So the point is, so we need imagination, and we need to be creative, but we also have to be able to let go, because that's the way science makes progress. And so it's this imagination, but not getting too attached to our ideas. They're both kind of have to go hand in hand so that the science can make progress.
Awesome.
Well, one thing I would add, Nathan, actually, just thinking about the analogy with metaphysics, is that as you're doing the proto-sciences, as before, we can do the experimental test, you do have the consideration of like a sort of economic cost benefit analysis. So what am I assuming? That's my cost. And what am I explaining? That's my benefit. So if I find that my explanatory virtues are high compared to my costs in terms of assumptions, then I think people will take ideas, at least take them seriously. And I think, that's where the battles are. Like if you take something like string theory versus loop quantum gravity, some people would say, well, string theory has to assume more. It has to assume, supersymmetry and extra dimensions. Loop quantum gravity doesn't need any of that. But then you might say, well, okay, yeah, but we get more out of it. The superstring theory is like a theory of everything. It can explain all the forces. Loop quantum gravity is just like a theory of gravity. So that's where, there is some sort of subjectivity here, but it is using the same sort of tools that you would use in philosophy and metaphysics, of like explanatory virtues versus sort of the cost of assumptions. So there, I think there is some similarity.
Mm-hmm. Awesome. So I was wondering then, for both of you, the whole kind of book is framed against the backdrop, I guess, of partly religion and partly kind of like almost cultural myths of origins and things like that. I mean, what do both of you think the relationship is between the cosmology and the science and what it has to say, and I don't know, cultural myths of origins and explanations, and religious stories or theological understandings and explanations as well?
Phil, you go first.
Okay. Well, I mean, there are obviously, we do draw parallels between some of the scientific ideas and old ideas in philosophy and in mythology. So, you know, we recently did a discussion with like Hugh Ross, who says like the Big Bang's in the Bible. And maybe you can say it is, but you can probably say it's in almost every creation myth, because you can always find some similarities. Like the idea of this, you know, sound waves that are going through the universe. There are creation stories coming from the East, you know, from Japan and China and India, of like a primordial hum. You know, you go to a yoga class and they say Om, and that's supposed to be like this primordial hum. So you can make analogies, and sometimes they're kind of fun to think about. We should also remember that, you know, there are sort of tribal warfares that exist in science. They're part of human nature, I would say. I think it's part of human nature, unfortunately, to be tribal. And we can't really escape that. I mean, we try via doing science, but we have to remember that science is a human process. Coming on to some of the religious claims, you know, we talk about the Kalam cosmological argument, and in particular, because that's very relevant here. The claim, there's a whole, in fact, it was very, you know, cosmological arguments were voted the best arguments for God in the Phil Paper survey. Whether it was a Kalam one or not, I don't know. It didn't specify. But similarly, actually, Sean McDowell, he just did a video like, what are the best arguments for God? And cosmological was voted #1. But this is predicated on the idea that the universe had a beginning and that it must need a cause. And what we sort of try and explain in the book is that we don't know whether the universe had a beginning. It might have, you know, we don't claim to know the opposite is true, but it's certainly possible that the universe always existed. So we think that the Kalam cosmological argument is invalid in that sense. Moreover, even if it did begin, it's not clear that it would need a cause. So there's lots of models that we talk about where maybe time doesn't exist, or time moves in a circle, or, you know, there could be extra dimensions of time. And so all of these ideas would threaten the notion that there's a cause to the universe. So from that perspective, then people shouldn't use discoveries in cosmology that are premature to sort of bolster religious arguments. In fact, what's really ironic is Lemaitre, who was one of the originators of the Big Bang, argued very strongly against this. He didn't want it used in any kind of religious debate. And
he was a priest, right? So that's
sorry, he was a Catholic, as well as being a cosmologist. He was also a Catholic priest, and he actually had an audience with the Pope. The Pope had used the Big Bang as sort of proof of the fiat lux, you know, let there be light. And Lemaitre was like, no, shut up, you know. So he had an audience with the Pope, and the Pope didn't mention it again. And what we don't know exactly what was said in this meeting, but I think it's reasonable for us to conclude that he advised the Pope to shut up. So that's on the religious side. But on the atheist side, you know, I think there have been some, you know, people like Lawrence Krauss who have been sort of premature in sort of saying we could have a sort of naturalistic universe from nothing. And maybe you can, but we talk about those models in the book, but they're certainly not observationally tested. And in fact, right now, I don't think we know of any way to test them. So similarly, then, it looks like the overconfidence of religious faith, I think, you know, people making too brash statements. Hawking did the same, you know, that we can show the universe came from nothing. And it's like, no, we can't. That doesn't mean it didn't come from nothing. Maybe it did, but we certainly don't know that. So there's overconfidence on both sides of this debate. And what we try and argue in the book is for caution. Caution balanced with optimism that, you know, one of these ideas that we explore might well be right. But you've got to keep those two in balance.
But a scientific attitude, you might say. Is there anything you want to say on that, Niayesh, or not?
Yeah, so I think this is obviously a very, very fascinating topic. And I'm not sure exactly Phil and I quite agree on this, but I mean, we have come to a compromise, at least in the book. But it's, I guess the way I would like to phrase it as both, I mean, there are ancient religions, but there are new religions about how the universe was created. And then they might have different languages, but some of them may be not very founded in evidence. That might just be beliefs. So I think what I draw from this is that, okay, so that there is science and religion have been basically both parts of humanity for thousands of years. I mean, I don't think we're going to separate them from each other. I think they're going to, we may change their names, but the same tendencies that led to religions and religious kind of developments and attitudes, and to scientific development and attitudes, they are within our societies, and they're intertwined. So I think we should kind of learn to live with it, with both of them together, and in peace and harmony as much as possible. I don't think we could kind of get rid of one or the other, but we should just kind of try to make their coexistence as peaceful as possible under whatever name and guise that they have.
Awesome. So then I guess final thing then from both of you would be, where is the best place for people to get this book from if they're interested, and where can they find out more about both of you?
Well, you can buy the book on all good booksellers. Amazon, of course, sell it. You can get it on the University of Chicago Press website. In the UK, we have booksellers like Foyles and Waterstones. Order it there. And if you like the book, please, please, please give it a 5-star rating on Amazon, or give us a review if you like it. If you don't like it, don't. So, and then to find me, I'm on YouTube, Phil Halper, and Niayeshi has his website, NiayeshiAfshordi.com, isn't it?
It's nafshordi.com, and you can read my papers. I don't know that you probably find them boring, but I do write professionally on physics and astronomy and medical physics and everything physics related that you're interested in.
Awesome. I'll put the links to all that stuff in the description. Thank you both for coming on.
It's been great. Thanks for having us on, Nathan.
Thanks, Nathan.